afternoon, everybody. Hopefully the week is going well. I wanted to start with a little bit of info. So the first homework will be out this Friday. And it will be posted on the course website. And it will be due the Friday after. And there will be instructions on how to get it in. Okay. So that's the first piece of business. Let's see. So on Monday, we started with a recap of a lot of what we've done in the course, and then we ended with this idea of n-chains, which are functions from the collection of n simplices to the integers, and that we're going to write as these expressions. Okay, so those were the n-chains. We also, right, so the collection of n-chains rather, so Cn kz is the set of all things that look like this. Okay. Then we also defined the boundary operator, which is a function from here to here. And the way to do it is enough to define it on n simplices and then extend it linearly. And we also talked about equivalence relations. And one in particular that is super, super useful is this idea of the path-connected components of a simplicial complex, or of a graph in particular. So the main example was path-connected components. And we ended on the note of thinking about the following sequence of chains. So C1, C0, and then 0. So this is the first boundary map, is the 0th boundary map. And what we saw was that if you take two vertices, say ui and uj in K0, so two vertices in the simplicial complex K, then what we saw was that I want to put it like this: if ui and uj are in the same path-connected components, or the same path-connected component, from now on, I'm going to write, or at least for the next 5 minutes, I'm going to write being the same path-connected component as the following: ui squiggle uj. Right? So that's going to mean that these two vertices are in the same path-connected component. So we saw that if they are in the same path-connected component, then when you look at the chain uj minus ui, then you realize that you can write it as delta 1 phi for some phi in C1 kz. Okay? So just to be completely clear, we're taking two vertices. then we can think of uj minus ui as just a zero chain in here. And what we saw was that if these two vertices were in the same path connected component in the underlying graph, then the following chain is actually delta 1 for some phi. And the way we constructed phi, I think I used tau last time, but the way we construct phi is by looking at a path connecting ui and uj, and then just taking the sum of the edges as your phi. Okay, so that's what we did last time. I want to consider the opposite question now, and I guess I wrote these appropriately. So here we said that if they are in the same path connected component, then their difference looks like delta 1 of something. I want to go back. I want to say, what happens if this is true? Is it the case that ui and uj have to be in the same path connected component? So that's what I want to do now. Okay? So I'm going to do it this way. So say that uj minus ui is equal to delta 1 phi for some phi, for some one chain. So when we did this, we chose a very particular chain, and now I'm just going to say, let's just say that there is one. We don't know what it is, we don't have control over it. Let's just say that there is one that does that. We're going to try to see whether or not uj minus ui, whether ui and uj, the vertices, are in the same path connected component. Okay? So here's what I'm going to do. So let's imagine our complex K, maybe perhaps something like this. And then what I can do is I can name the path connected components. So let's name them maybe K1, K2, all the way up to Kp. So each one of these guys is going to be a path connected component of the complex K. Okay? So the thing to notice is that if I have a one chain in here, then I can write it as follows. Ep, where phi1 is in C1, K1, phi2 is in C1, K2, and phi p is in C1, Kp. Okay? So what's happening here? I'm taking my simplicial complex K, and I'm taking one chain in it. So what is that? It's just an expression that looks like this, where these guys are edges, right? One simplices, they're edges. Now, I can, by rearranging, I can put all the edges that are in the first part connected component, then I can take what remains, then put all the edges that are in the second path connected component, and all the way until I run out of edges, or out of path connected components. So that is what this expression is saying. Okay? So now, let me use this gadget right here. So I'm saying that uj minus ui is equal to delta 1 of phi. Okay? But now we've written this expression, so I'm just going to put it aside like that. And by the way in which we define the boundary maps, one can see that they act linearly, meaning that I can split this sum. So this is equal to 1, 2, and all the way up to p. Okay? Because the way we defined delta 1 was on each simplex individually and then adding up the results together. so here's where we need to do some thinking. Notice that this chain over here, let's say phi1, is entirely contained in the first path connected component. Okay, and let's look at phi2 for example. So all the edges are contained in the second path connected component. So when I compute the boundaries, the only cancellations that occur are within each path connected component separately. There are no cancellations across because there are no edges. Okay? So if this is to be equal to this, then the only way that can happen is if either there's only one path connected component that results in these two terms, or there are, let's say, two, and then this, let's say, corresponds to that, and this corresponds to that. Okay? And then all the other ones need to be zero. There's just no other way. Okay? So this has to be equal to delta 1, let's say phi, sort of ki plus phi of kj. And here ki and kj are between 1 and b. Okay. So that can happen. That is sort of situated. That's not the case, the first case, so case 1, where the boundary of these gives you this, and the boundary of this gives you that. And then the second case is that it's just one of them. So uj minus ui is equal to something between them. Does that make sense? Okay. So let's think which case is possible. Let me ask first if it makes sense what I'm asking. So I guess it doesn't hurt to go over the argument again. We are trying to see whether or not this condition, meaning that uj minus ui equal to delta 1 of something, whether or not that implies that these two vertices have to be in the same path connected component. That's the goal. Okay? So we start here. The first thing we do is say, okay, take this one chain, it is whatever it has to be, but the thing that we can do is write it as a combination of smaller chains, where I'm only taking I'm taking the edges that appear in here, and just putting them in the appropriate path connected component. That's where these 1 through p come in, one for each path connected component of k. So we're here, and that's again what this conveys. So I'm just plugging in this guy instead of phi, and we get this formula right here. And then the next idea is to think that there cannot be any cancellations between expressions that appear from here with expressions that appear from here. The cancellations have to happen within, because there are no edges across. Right? So once you realize that, then there are only two possibilities. Either these two terms correspond to two of these guys and the others are 0, or everybody is 0 except one of them. So that's the second case. Okay? So if we are in this case, then we'll be able to say that they're the same path connected component. Right?
So one thing to be clear, so that equation, the last line of the first equation. So
this right here?
Above that one.
This?
Yeah, so there's no overlap.
There's no, exactly. So when you compute the boundary, let's say of delta of phi1, what you get is an expression in terms of vertices that appear in k1. When you compute the boundary of phi2, you get an expression with vertices only with k2. And when you add these two things together, there are just no cancellations between these two sides because there's no edges. Right? Yes?
I'm just curious because case 2 seems very similar to the original condition that we plotted out. So it's
Yeah. To this or to this?
To that one up there.
To this one. Right, so here we're saying case, the first statement is the difference is the image of a chain, but we have no control over which chain it is. What case 2 is saying is that the chain that makes everything possible is actually constrained to only one connected component. Right? And then from there we can conclude that these two vertices are indeed in the same path connected component, because this is the chain that binds them together in a way. Okay? So that's the difference between these and the statement.
Okay.
So the question now is which one of these two guys is possible? So let's see. So here's a useful thing to do. Yeah. So, and again, case 2, just to be very, very clear, what I'm saying here is that delta 1 of pki is equal to ui, and that delta 1 of pkj is minus uj. That's what I'm saying. Okay? Okay, so I'm going to show that this is not possible. This is not possible. And let's see how. So it is useful to think about the following function. So I'm going to take C0, KZ, and I'm going to map it to the integers. And the way I'm going to do that is via a function, let's call it E. And what it does is the following. It takes a zero chain. So what's a zero chain? It is something that looks like, N1 U I1 plus N2 U I2 plus ... NK UIK, right? So what is a zero chain? It's a combination of integers and vertices. Okay? So what is the function going to do? It's going to report the sum of the integers. Okay? That's what epsilon, that's what E is going to do. So it's going to add up together the coefficients. But we also have the boundary now from here. Okay? And here's what I'm going to check right now. Let's take a one chain in here, okay? And I'm running out of letters, but I'm going to take a chain in here, and I'm going to write it, let's call it tau. Okay? And let me write it, tau, as, N1, and then I have to put an edge here. So it's going to be a sort of a U, J1, U, L1, plus N2, U, J2, comma, U, L2, plus, and then M, D, This is how any one chain looks like in here, right? A bunch of edges and a bunch of integers in front of them. Let's now compute delta 1 of tau. Okay? So it's going to be let's see. M1 UL1 minus UJ1 plus M2 UL2 minus UJ2 plus MD ULD minus UJD. Okay? Now what happens when I apply E to this guy? So what is the result? What expression do I get here?
It's not.
So what do you have to do? You have to look at what are the coefficients that appear in front of each vertex and add them all together. Right? That's what E does. So you get 0. Right? Because these minus that, because everything distributes. So everything cancels out. Okay? So what I'm saying here is that if you start with a one chain, you apply delta 1, and then apply E, you always get 0. Cool? Let's now get back to this. So if case 1 were true, right? Then we would have that, for example, UI would have to be equal to delta 1 of VKI. And then when I apply E to both sides, what do I get here on the left?
0.
You get 1.
Oh, you get 1?
Yeah. What is the coefficient in front?
Oh.
1.
Never mind.
And what is the and what do we say over there that has to be 0? Right? The composition of E with delta 1 is always 0, whatever you do. So this cannot happen. Right? So case 1 cannot be. Does that make sense? So the only option is for case 2 to be what's true, which means that UJ and UI were part of a chain that is entirely supported on the same path-connected component. So this shows that. Right, so the conclusion is that UI and UJ are in the same path connected component. Yep.
Yeah, so I was a little bit confused in the fact that we already were trying to prove a theorem that said that if we were to take C1 to C0, that like if you take D squared, you always get 0, right? That's like the theorem that we're trying to.
We're getting ahead of ourselves,
Oh, okay.
right? So that is actually going to come later in the lecture today. Here we're doing something simpler actually. We are maybe not simpler. The first thing to notice is that since D0 maps to 0, then this composition is always 0 by design. So there's nothing there. The thing that we're trying to prove right now is whether or not this condition, UJ minus UI being the image of some phi, always implies that they have to be in the same path connected component.
Okay.
That's what we're trying to prove right now.
Yes.
What we showed is that that is indeed the case.
Okay.
And the strategy was, let's take whatever chain we're given and then construct a nicer chain, one that is supported in only one path connected component. And that's what
Okay, that's why
results.
case 1 was. If case 1 would have been true, then we would have disproven that claim.
Then the thing that we just computed on the left would lead to this contradiction.
Yeah.
Right? So that's why we get rid of this case, and the thing that is true is this case too.
Yeah. Okay, I'm sorry. I got it.
No.
My bad.
It was, there's several moving parts, but we got them all to work. Okay. So let me just say this. Right. So I'm going to use these P's right here. So what did we do? The first thing we did was to analyze these P's of chains and boundary maps. And what we showed was that if you take two vertices, then they are in the same path connected component, remember that we said we were gonna denote that by this squiggle. This happens if and only if the difference of the chains, of the zero chains, is delta one of phi for some phi in C1. Right? That's what we've shown. Okay? So what is the abstract? The abstract is by understanding this little piece of the collection of chains and chain maps, chains and boundary maps, we can understand what the path-connected components of K are. Okay? Great. Let's see. Okay, so this is a good place to think about the following. So I'm going to write this in a slightly different way. Okay? So let me do it over here. I'm gonna write it in the following way. So this is true, means that uj minus ui is an element of the image of delta 1. Is that cool? So right. The key elements again. This piece of the chains and the boundary maps, sort of the 0 and 1 portion, in this condition allow us a very good understanding of what the path connected components are. That's the main message. Okay. So what I would like to do now is understand the next step in the collection of chains and path and the boundary maps. So here's C2, C1, and then C0. So this is delta 1. Okay, and then in order to understand this portion, I think it's useful to think about the complex we had in the previous lecture. So we're going to put it right here. So the complex is this guy. U0, U1, U3, U2. This is tau 1, tau 4, tau 5. This is tau 3, tau 2. And this is sigma. And this goes like that. And then there were 4 chains that we thought about. So the first chain was phi1, which is tau 1 plus tau 2 plus tau 4. The second chain is phi2 plus tau 4 minus tau 5 minus tau 2. 3, phi3, which is tau 1 plus tau 2 minus tau 3. And then the last one was tau 4, which is tau 1 plus tau 4 minus tau 5. Right? So that was the example we had last time. Okay. And let's just put some words next to the chains. So what we had seen is that phi1, which is just tau1 plus tau2 plus tau4, meaning this guy plus that guy plus that guy, this is just a chain. Then phi2, which was tau4 minus tau5 minus tau2, is what we call a cycle, right, going around. The thing to notice is that we now have the technology to actually compute things about this chain. So let's say that we computed delta, the boundary of this guy. Okay? So what is the boundary? It would be, so we start here, we do this minus that, right? Then we go here, it would be this minus that, so this cancels out. And then it would be this minus that, so both of them cancel out. So hopefully you can check by yourselves that you get 0 if you computed the boundary of that cycle. Okay? Now, phi3 is tau1 plus tau2 minus tau3. So is this plus that minus that. So it looks visually as if it were the boundary of sigma. So we call this guy a boundary. And again, now we have the technology to actually compute things. So what is the case is that if you compute the boundary of sigma, you will recover this class. Okay? And if you look at phi4, right, so that's this plus that minus that minus that. So this is also a cycle. If you compute this boundary, you will get 0. But the more important thing is that if you do 4 minus 2, so this is the cycles, you would get phi3, which is a boundary. And the idea was that both this guy and this guy are essentially identifying the same hole in the space. So same hole. Okay, so that's the sort of example we had last time. And it's useful just to understand this piece of the construction. So there are 3 things that we identify as important. We identify the chains so that when you evaluate their boundary, you get 0. We're going to call those cycles. So we're going to let Zn of Kz be all the chains so that when you compute their boundary, you get 0. We're going to call these guys the cycles. And we're going to call Bn. So what is the second thing that we found? That there are some chains that are boundaries. Okay, so we're going to call these guys, so this is going to be the image of Dn plus 1. By the way, these are called n cycles, just to be clear. Cycles of dimension n. And these guys are really called n boundaries. And then the third sort of piece of the puzzle was that 2 cycles that code for the same hole, when you subtract them, you get a boundary. That's the third idea. Okay? So let's get let's get to this point. So at least for these guys, right? So let's say phi I and phi j in Z1 say code for the same pole if Vj minus Vi is Yep.
So this is an arbitrary notation question, but is in boundaries, is that z as in integers or z as
Yeah,
in
this is Z as
bytes?
in integers,
Okay.
correct.
Okay.
Yeah. Okay, so this is the place where we again try to put everything together. When we analyzed the 0th part, we were talking about path connected components. Now that we're looking at dimension 1, we are looking at holes in the space. Okay? And then the relation that seems to be important is whether or not the difference is a boundary. So we're ready. We're ready to define what homology is. We've done that in 2 very specific cases. Before I do that, let me say 2 things. Yeah. So the first thing I'll say is that if you compute the 0th chains, so this is a remark. So where are the 0 chains? The 0 chains are the ones that when you apply the 0 boundary, you get 0. Right? So if you go here, you see that all 0 chains go to 0. So everything in here is a 0 cycle. So that's the first sort of easy statement. The second is a little bit more involved. I'm going to call it a theorem. And the theorem is that, because this is what Joe was referring to, is that anytime you concatenate 2 of the chain maps, you get 0. Right? So if you go first with delta 1 and then with delta 0, okay, you get 0. That is not surprising. Here it takes a little bit more work, but hopefully one can see that if you have a simplex and you compute its and it's oriented like that, and you compute its boundary, and you compute the boundary again, then they cancel out. Hopefully those pictures make sense. Right? If you compute the boundary of this guy, then you get this edge plus that edge minus this edge. If you compute the boundary of this thing, you get this minus that, so these 2 cancel out. And then if you do here, you get these minus that, so these 2 cancel out, and these 2 cancel out, so it's 0. Okay? And what I'm saying is that this is true for all n. So let's just do it. This is one of those things that when you see them for the first time, you're like, why? But it is useful to see it at least once. So it is enough to check that delta n plus 1 evaluated on an n plus 1 simplex for any n plus 1 simplex sigma. Right? So if you just do it for 1, you'll be okay. Why? Because now this is defined. If you do it in a more complicated n plus 1 chain, then you can just break it into n plus 1 simplices, and if each one of them is 0, then you're good. So let's do this. Okay? And I'm going to do a proof by picture, which you're not supposed to do when you're writing math, but we're gonna do it here because it's enough to understand the idea. Okay, so what is the proof by picture? So say that we have your n plus 1 simplex here. And the first thing we do is we compute the n plus 1 boundary. Okay? All of it. That's the first thing we do. So what does that process entail? So the first thing you do is you remove the first vertex. So here we remove 0. And you get u0 hat u1 double dot un plus 1. I'm going to isolate two places here in the middle. And I'm going to just analyze what happens to those two places. So I'm going to let I, so 0 less than I, less than j, less than n plus 1. So I'm isolating the I and the j places. So you do these for all the next ones. Then we remove I, correct? So this is plus, plus, plus. When you remove I, you get minus 1 to the I, u0, ui, hat, and then un plus 1. At some point, you remove j as well. So plus, plus, plus. Minus 1 to the j, u0. A little more space. Then here's j. We remove that guy. Un. And then plus, plus, plus. So minus 1 plus u0, un plus 1. Okay? So that's the first step. You remove each one of the vertices to go to the boundary map. So here we remove n plus 1. Now I'm going to concentrate on these two guys. What I'm going to do next is I'm going to apply delta n. Okay? And you go through the same process, right? So for this guy, you remove 0, 1, 2. When you get to the jth place, right? To the jth place, we're going to remove j. Say that you have u0, ui hat, dot dot uj. We remove that guy, un plus 1. What is the thing that is in here? What is the coefficient that I get? We're paying attention. I plus j. Does everybody agree? Is that the right answer?
I minus j?
Minus 1.
Oh.
Let me explain why. When you removed I, j was moved one spot to the left. So this is the minus 1 that will appear. Correct? So that's that. Let's check this out. So here we're going to we'll do all the removing, and at some point we remove I. Okay? What is the coefficient that is in front of it?
J plus I minus 1?
Wrong answer. I plus j.
Yeah, exactly.
Because you haven't removed anything that affects this guy.
Oh, J's after I.
J's after, right? So notice that these two guys cancel out. Right? Because another way to write it is remove this minus 1 from here and just put it in front. So now this guy cancels with that guy. And the argument is that if you do the same everywhere, you can pair everybody and cancel things out. Yeah, I I think I'm not gonna attempt to write it in detail, but hopefully this is enough. The idea of the proof is to just concentrate on two pairs of indices at a time. Let's say, let's see what happens to I and to J down the line. And what you see is that they give you pairs that always cancel out. And it will be true for all the final terms that appear in this expression. And that's why the entire thing will be 0. If you're not convinced, I would suggest taking n to be 2 or 3. And just going through the exercise of writing out the final expression and seeing that indeed you can pair things out, you can pair things up and that everything cancels. Good? Yeah?
Just one little question.
Yeah,
So
go ahead.
for each procedure, you say remove I of J's
Mhm.
element, but you write like a new I and the height. What does that really mean?
Yeah, so throughout this process, I and J are the same I and J that I fixed at the beginning.
Okay.
Okay? So the first thing I do here is remove the I spot, and that gives me this I hat.
So what does that
Oh, what does this notation mean?
Yes.
Oh, this notation means, it's actually useful to remember. U0 through UI hat plus 1, I guess. These, we defined it to be, just take the entire set and take out the I
Oh, okay.
element.
Okay.
Yeah, this is the notation.
Okay. I see.
No, thank you for giving us an opportunity to remind ourselves. Okay? That's how the boundary maps are defined. Okay? So again, this may be confusing the first time you see it, but if you do it for a small n, I'm sure you'll be convinced. N equals 2. Perhaps we'll be inspired and we'll do it during the homework. Okay, so that's the proof. But the important conclusion is that the boundaries and this is what really is important, is that if you look at the boundaries, so these are the things that look like delta n plus 1 of something. If you apply delta n to them, you will always get 0. So what it means is that every boundary is a cycle. And now we're in business. I erased a bit, but that's fine. Okay? So now we're ready to define the big gadget. So we'll start with the following. Define, so let be the relation of Zn KZ given by phi1 is equivalent to phi2 if and only if, or related to phi2 if and only if phi1 minus phi2 is in Vn. And hopefully this is familiar now. This is a relation that we've seen from the beginning of the class to be the thing that is keeping track of connected components, cycles, and holes, and so on. So we're going to look at that relation more closely now. And the first thing we're going to see is that it's in fact an equivalence relation. It's an equivalence relation. So why don't I give you a couple of minutes to convince yourselves that this is the case. So you have to prove that it is reflexive, symmetric, and transitive.
Reflexive is just zeros in the null space.
Yep, that's always the case, right? So phi minus phi is equal to 0, and that is indeed, that is equal to, delta n plus 1 of 0, which is certainly in the end. So that was the easy one. Symmetric, right? So if phi1 minus phi2 is in here, right? That's what it means for them to be related. Then it means that they're equal to delta n plus 1 of something else. Let's say psi. Okay? And then if now you flip, the way we've defined things, you will see that it is true that this holds. Okay? You're just flipping orientations everywhere if that's how you want to think about it. Transitive. So phi1 minus phi2. So if these two guys are related, that means that they differ by something.
And then if you have a P3 as well, so that's the
P2
It's something else, right?
And obviously,
And if you add them up,
yeah, they just give you one.
is true by linear.
yeah, again, the way we defined these boundary maps, they were linear by design. Right? So psi plus psi prime. And check. So it's an equivalence relation, okay? Okay, cool. So what do we have? Let's put all the pieces together. Okay, so here we have, Cn plus 1, Kz. Okay? Inside it, maybe let me do it here. Here we have Cn, Kz, and here we have Cn minus 1, Kz. Okay? We're going to put all the pieces together now. So delta n plus 1, and here's delta n. Now, inside Cn, there's all the things that map to 0. So let's put them here. How did we call all the things that map to 0?
Kernel.
Yeah, but in here, in topology. Cycles, right? Cycles. So these are the Cns. And what did we prove here? We proved that the boundaries, which are the image of the previous one, fall something somewhere here. Right? So these are the ENs. Boundaries. Okay? Now, notice that 0 is a boundary, right? Because it is the image of 0. So 0 is right here. So that means that if I look at the equivalence class of 0, it is hopefully not hard to check then you get exactly the boundaries. Right, so this is the equivalence class. These are all the things that are related to zero. Okay? How do we see that? The things in here are so that 0 minus the thing is in the boundaries. So that implies that the thing is a boundary. Okay? So we have that. Also remember that every time we have an equivalence relation, it partitions the set into equivalence classes, disjoint equivalence classes, right? So these are all the different equivalence classes we get via this relation. We're going to call, and here's the most important term of the day, we're going to call these classes homology classes. Okay? So here's the definition. Define, let Hn Kz be the set of equivalence classes. And I guess one way to denote that is like so. So this is called the n-dimensional homology. And you are probably tired of writing Z. The reason why I've been keeping track of it all along is because later on we're going to replace Z by other things, which are going to actually be computable in the computer. But for now, we're going to keep it as a reminder that it's something that may change in the future. So let's talk. Let's talk a little bit. Okay. I'm going to write something down and you tell me what your intuition says it captures. Okay. So let's say that I were to compute H0 of a simplicial complex. What is this measuring? What are the different equivalence classes measuring?
Different points.
Different points. Anyone else?
Oh wait, sorry, points.
Sorry. Classes. Okay. Next one. So H0, right? So what are we measuring? We're saying C0 going to 0 and C1 coming into it. Okay? That's the H0 computation. So we're saying stand at C0 and look at the classes that differ by something from C1. That was the first thing we did today. Path connected components. That's what it codes for. What happens if you compute the next one? So you're looking at C1 going into C0, coming from C2, right? So these are one chains which form cycles that do not bound things. So these are holes, right? These are holes, one-dimensional holes. Okay. And we'll have a chance, I guess right now, to actually see this in practice. So let's just do some calculations to get ourselves acquainted with these two objects. The higher dimensional ones, hopefully you can see that they code for higher dimensional holes, right? Because if we're to compute H2, now you're looking at chains made up of triangles that go around. If you're looking at H3, you're looking at tetrahedra that form cycles and so on, right? Yep.
So are these holes similar to like the ones when we discussed Betty numbers and stuff like that and circling those? Are
Yeah,
they
yeah.
similar dimensional holes?
Exactly right, exactly right. There's actually a very close relation between these guys and Betty numbers. I don't think we're ready yet to say what it is, but they measure how big these guys are. Okay, so let's do a couple of examples just to get ourselves acquainted. Yeah. So let me put it here. Let's do the following. I'm going to consider 3 different complexes, and we'll compute these groups. Sorry, these sets for those complexes. Okay. Yeah, this is okay. Okay, so the complexes in question are going to be K0, which is just going to be an edge, you know, with the vertices 0 and 1, and just an edge called tau. The next complex is going to be a little bit more complicated. So we have U0, U1, and U2. Tau 1, tau 2, and tau 3. And the next complex we're going to look at is the filling triangle. Okay. And this is sigma. Okay, so what is the intuition for these 3 complexes? How many path-connected components do we have in each case? We have 1 path-connected component in each case. How many holes do I have in K0? There are no holes. In K1, there's supposed to be this hole. In K2, there is of course this cycle, but that cycle is filled in. There is a boundary, so there are no holes in here either. Okay? So hopefully that will be reflected in the computation we do now. Okay? So let me start with what the chains are for each example. Okay? So in this example, we have, of course, C0. We have C1. So C0 is going to be combinations of these 2 vertices. C1 is going to be just multiples of this edge. And then there are no higher dimensional objects. So just zeros after that. Okay? For this guy, the same situation applies. So C1, sorry, C0, C1, and then zeros. And then for this guy, we have, in fact, C2, C1, C0. Okay? Let's start with C0. And I'm going to, I'm not going to write KZ now, just to save a little bit of space. So what is Z0? So C0 is all the things that look like M U0 plus L U1, and here M and N are integers. Agreed? So those are 0 chains. Okay? Now, notice that if I start with a 0 chain like this, so let's put it here. So M U0 plus L U1, I can always write it as follows. I can write it like M plus L U0 plus L U1 minus U0. Agreed? Add and subtract the same thing. All this trick in mathematics. So another way to write this is as M plus L U0 plus L times the boundary of tau. Correct? So what we found is that this chain, sort of an arbitrary zero chain, is always equivalent to a multiple, to an integer multiple of u0, because I have the leftover boundary, right? In other words, this minus this is a boundary. So these two classes are equivalent. So the conclusion from that computation is that in K0, right? In K0, any zero cycle, right? Because any zero chain is in fact a zero cycle, is of the form, is equivalent to one of the form let's say n u0. And n is an integer. I guess here, this is what I'm calling n. Okay? In other words, h0 of k z is in fact the set that looks like n u0 and okay. If this looks strange to you, this is the time to ask any question. Okay? So let me perhaps say a few words about this computation. So I started with C0, which again we know is equal to Z0, because we always go to 0 afterwards. So what are we trying to do when computing homology? We're trying to see when two cycles differ by a boundary. Okay? So what I did here is I took any arbitrary zero cycle, something that looks like this. And then by algebra, I was able to write it as an integer multiple of u0 plus a boundary. It means that any zero cycle is of the form integer times u0, which in particular says that the homology in degree 0 is just integer multiples of the class of u0, of that vertex. Okay? So, and this is cool. So it's saying that as a set, this is essentially, take u0 and just multiples of it, right? Just integer multiples of it. Another way to write this is that this is essentially z. Okay. We're going to do one more computation, and hopefully it'll be clear. Let's do two computations. So let's compute h1 of kz, of k0. Z. Let's try to do that computation. Okay? So so what do I have to do to compute h1? I have to stand here in degree 1 and first compute the 1 cycles. That's the first task. So I need to compute the 1 cycles of k0, and then look at the equivalence classes by the relation of differing by a boundary. Okay? So question, what are the 1 cycles in here? Let's see.
Oh no, there is one.
The zeros. Right. So what is Z1, K0, Z, right? So this is the collection of all the one chains, right? So what are the one chains in here? These are just integer multiples of tau 1. So these are the things that look like n tau 1, integer multiples of that, so that when you apply the boundary, you get 0. Okay? And the only thing that does that is 0 itself. Correct? So that implies that h1 of k0 is 0. There's only one class, the class of 0. Maybe that's good to write it at least once. Yeah?
I just wanted to say, so H0 in general, that's gonna be like isomorphic to Z to the N, where N is the number of connected components we
That's
have.
exactly right. That's exactly right. Yeah. The comment by Matthew, was it? Yeah. That was that what happens if K0 has more than one path connected component? What you will notice in the computation is that you are going to get a bunch of copies of Z, like you're going to get like Z times Z times Z times Z, as many as path connected components the space has. That's how we detect shape. That's a very good point. It's harder to see, but a very good point indeed. Yeah, let's do this computation for K1. Okay. So hopefully you believe that K1 is just Z, right? It's got one path connected component. One can actually go through the process of computing it and realize that it'll look something like this at the end. But let's do the one that is more interesting in this case. Let's do that one. Okay? So for that, we need to compute the cycles of K1. And then take the equivalence relations. That's what we need to do. So what is Z1? So let's say N tau 1 plus M tau 2 plus L tau 3 is Z1, if and only if, when I compute the boundary, I get 0. And let's try to see what the relations are between N and L. Okay, so this is equal to N times, what are the, can you guys shout out what the boundary of tau 1 is? So I don't have to keep moving.
U0, U1.
U1 IC0.
Okay, how about tau 2?
U2 IC1.
And how about tau 3?
U2 minus U0.
Thank you. U2 minus U0. Okay, so this is equal to, let's do some algebra. So this is equal to N minus M U1 plus M minus L, there's an error. No, that's fine. N plus L U2 plus, and then U0, right? And then L minus N U0. Minus and plus. Does that look right?
Yes.
Okay. So if something funky. Okay, so the ones are N and M, the 2's are M and L, and the 0's are minus L and minus N.
Oh, do we need a negative sign because if we're going around a certain way? Because for
No, I mean, we expect, that's your geometric intuition talking. You're saying that the cycle should be something that goes like this with a minus sign in here. And I'm just saying, take any chain, and let's see when it is a cycle.
okay.
That's all I'm saying, right?
Oh, okay. Oh, yes. Okay. I see. Okay.
So, but that's good. It sounds like the geometric intuition is taking hold. No, maybe we're fine. So if this is gonna be equal to 0, right? Then the condition we get is that n has to be equal to m, right? And that L has to be equal to minus n and minus n. Correct? So it's the cycle. It's a multiple of the cycle that we thought we should get. So let me write it over here. 5 minutes. So if that is true, then indeed, let me put a name to this guy. Let me call it phi. Then phi is in fact equal to n times tau 1, tau 2 minus tau 3. Right? Which is, again, the cycle that we've identified before. Now, what is B? What is B0? Sorry, B1. It's 0, right? Because nothing non-zero will map here, starting from 0. In other words, the first homology of K1, with coefficients Z, is going to be essentially all the things that look like, n times phi, tau 2, tau 1, tau 3. Correct? Which again is the thing, is just integer multiples of these very particular cycle. And again, this is Z. And using Matthew's intuition, if we had more holes, we would get more copies of Z. Okay? And then for the final computation in the last minutes, let me tackle this guy. Okay. Oh, by the way, hopefully it's not hard to see that this is true, right? Because there is no 2 cycles. And then for the final computation. For the final computation, I want to do H1 of K2. That's the final computation. Okay? So it's, as before, it's going to be cycles made out by this relation of different by a boundary. The same computation holds. Okay? So this is still equal to, things that look like n times tau 1 plus tau 2 minus tau 3, and then n being an integer. And then we have to divide by the relation. But oh, snap. This is equal to n delta 2 of sigma. And there's only one class then this is the entire boundary. So there's one class, the class of the boundary, which is the class of 0. So it all works out. It's sort of beautiful in a way how the algebra really takes over the geometric intuition. My suggestion and recommendation is, the first time I saw homology, I was very, very confused for a while. So don't get discouraged if these ideas seem foreign to you. Just try to do, several examples, just small computations like the ones we did right now. And in the homework, you're going to have the opportunity to repeat those computations just to get comfortable with it. So just to finish up. So we started the week with this recap of how do we measure the shape of data, right? And the first thing we did was this idea of clustering and the graph Laplacian as a vehicle for doing that. We also saw that the graph Laplacian was related to cycles, but beyond that, not much information could be obtained. And that's when we introduced sort of a harder, more involved gadget, which are these homologies. And the way they are defined is by looking at cycles of any dimension. And now the word cycle is not geometric anymore. It's an algebraic thing, right? Cycles. But hopefully the geometric intuition still remains. And then if we want to account for many cycles describing the same whole, that's where we cut out these boundaries. Okay? So let's stop there and have a good rest of the week. We will talk